November the 8th, 1985. 4 large but transportable satellite receiving dishes are on their way to Geneva. 2 weeks later, on the second day of their summit, the leaders of the world's 2 most powerful countries met for further talks amidst the usual glare of media publicity. Through British Telecom International communications links, American, British and European television stations were able to send these historic pictures to viewers throughout the Western world. Signals from the television company's outside broadcast units were fed to the dish aerials, which beamed the signals to a satellite in orbit over the Atlantic Ocean. Inside the satellite, the signals were amplified and then retransmitted to a ground receiving station in the United Kingdom. From the ground station in Herefordshire, signals were relayed by microwave links to the British Telecom Tower in central London. From here, the signals were passed to the television stations by landline. The signals were also relayed via another satellite to the United States. It is, of course, the television pictures that tend to make the headlines, but in fact, they make up a relatively small proportion of the information that's relayed by satellites. Telephone calls, facsimile and data transmissions, international telexes and video conferencing, and a range of other business and maritime services make up the bulk of satellite communications. Yet the technology which brings us these pictures from almost anywhere in the world is not that much older than these science pupils attending a South London school. They're becoming involved themselves in satellite technology as part of their science course. David.
Hello, Tom.
Isn't it unusual that a school should be experimenting with satellite reception?
No, not really. There's quite a few schools in the UK who use satellites in their curriculum. It's not particularly difficult and it need not be all that expensive. We're looking here at a picture from Meteosat, which we took about 5 minutes ago. It shows the UK quite nicely. You can see the outline just there.
The ability to transmit information by means of electromagnetic radiation was first demonstrated by the Italian scientist Marconi. In 1901, he made the first transatlantic radio transmission. Now, the part of the electromagnetic spectrum that can be used to transmit information ranges from waves of 15,000 meters in length to 15 centimeters in length. When Marconi made that historic transmission, he did so using radio waves with a fairly long wavelength. Waves of this length tend to follow the curve of the Earth's surface. However, waves propagate less efficiently over land, where hills and buildings weaken the signals. Marconi succeeded in part because his transmission was across the Atlantic Ocean. In the early days of radio broadcasting, it was largely this long wave part of the spectrum that was used. That is, from about 200 kilohertz to 1500 kilohertz, or 1.5 megahertz. The upper part of the electromagnetic spectrum was left to the amateur radio enthusiasts, who soon found that their radio transmissions could travel very considerable distances. Waves of higher frequencies, that is between 3 megahertz and 30 megahertz, can travel further, but not because they follow the Earth's surface. About 300 to 400 kilometers above the Earth are layers of ionized or charged particles. They make up the ionosphere, and it tends to refract radio waves. Radio signals of certain frequencies are refracted so much that they're effectively reflected back to the Earth again. They then bounce off the ground back to their ionosphere and so on. While such waves can travel considerable distances, the ionosphere is not a very reliable reflector. It can change from day to day, and it can be severely affected by the sun. In order to transmit radio signals reliably over long distances, we need a sort of man-made reflector above the Earth. In 1945, the science fiction writer Arthur C. Clarke suggested that it was theoretically possible to achieve reliable worldwide communications by placing 3 space vehicles in orbit above the Earth. These space vehicles could be at such a distance from the Earth that their angular velocity would be the same as that of the Earth. They would be in what is now called a geostationary orbit. The space vehicles would effectively hover over the same part of the Earth's surface. 3 such vehicles could provide communications between any 2 points on the Earth. 12 years later, the first step towards that visionary idea was taken. In 1957, the Russians launched the first Earth-orbiting satellite, Sputnik 1. At this time, the launch power of rockets was limited. Early satellites could only be put into orbits relatively close to the Earth's surface. Now, any body which is traveling in a circular path is constantly accelerating. And as it is accelerating, there must be a force acting on the body. That force, as you probably know, is called centripetal force. This force is directed towards the center of the circle. In the case of a satellite, that force is directed towards the center of the Earth. The magnitude of the force is given by mv squared over r. Now, in the case of an Earth-orbiting satellite, this force is provided by the gravitational pull between the Earth and the satellite, and is given by the gravitational constant times the mass of the satellite times the mass of the Earth divided by the radius of the orbit, squared. So, we can write the equation mv squared over r equals gmm over r squared. We can rearrange this equation to give v squared equals g times the mass of the Earth over r to find the velocity. From this we can see that the square of the velocity of a satellite is inversely proportional to the radius of its orbit. So, a satellite which is in relatively low orbit will be traveling at a relatively high speed. Indeed, the early satellites completed an orbit in less than 90 minutes. From the point of view of an observer on Earth, these satellites crossed from one horizon to another in about 20 minutes or so. Not yet what Arthur C. Clarke had suggested, but the first commercial communication satellite was in just such a low orbit. Telstar was traveling in a low orbit at nearly 20,000 kilometers an hour. It would be visible for only 20 minutes. Tracking the satellite with an aerial which weighed 1,100 tons was no mean feat of engineering, but it worked.
Here we are. Here we are. There's a bar. Now, we are that's a man's face. There it is. There it is.
Telstar was in a low orbit around the equator. Although it could only link America and Britain for short periods, it was, in engineering terms, a great success. Today, low-orbiting satellites are still in use. They orbit between 500 and 1,200 kilometers above the Earth, crossing both the North and South poles, and take about 2 hours to complete a single orbit. Polar orbiting satellites are largely used to gather geological, meteorological, and agricultural information. They're also being used for educational purposes. Here, David Grace and his pupils are waiting to receive signals from EUOSat, a polar orbiting satellite controlled from the University of Surrey. The satellite, designed specifically for educational purposes, orbits about every 90 minutes, about 600 kilometers above the Earth. It's visible from Britain about 4 times a day, for periods of about 15 to 20 minutes. David, do you need very complex equipment to receive these signals?
No, not at all, Tom. We're using a relatively cheap crystal-controlled receiver. It's locked into the satellite's transmit frequency, which is 145.825 megahertz. The aerial that we use is very simple dipole on the roof. You just plug it in and away we go. It's made out of very simple materials, aluminium tubing or aluminium rod. This receiver comes with an aerial, but you could, of course, make your own. It's not at all difficult to do. This is a very simple aerial. It's connected to a source of radio frequency waves. It's emitting electromagnetic waves in all directions at right angles to the aerial itself. We can use these to detect those waves. The light bulb gives us an indication of the strength of the electromagnetic field at any point around the aerial. Let's pass it round. Here you are, Lucy. Now let's pass it round and note the brightness of the bulb as it goes round. That's it. Right, over to me, Val. Thank you. Now, what I'm going to do now is add a second element, identical to the first, but not connected to the signal generator. Now let's try the same thing again. Here you are, Lucy. Now, can you see it's brighter? Right, pass it round slowly, not too fast. Now, when it gets round to Susan, It's got a lot dimmer, if not completely out. There we are, hold it. Right, on to Bal. Now it's gone on again. Right, thank you, Bal. Now, that time, the field was a lot stronger over here.
This illustrates the concept of the gain of an aerial. When we speak of gain, we mean the increase in the strength here of the aerial with the reflector compared to the aerial without the reflector. This applies not only to aerials when they're transmitting, but also when they're receiving. Hence, an extra element on the aerial on the roof would help in receiving the signals from USAT. The satellite is transmitting a string of binary numbers, or a bit stream. The information contained in this bit stream is decoded by the BBC computer. Thank you. This gives us information about the satellite itself, such as the temperature on its various surfaces and the status of its power supplies. The satellite is also sending back results of various experiments. Such satellites can't provide the sort of global telecommunication system that Arthur C. Clarke had envisaged. In order to do that, satellites have to be placed in a much higher orbit so that they'll have the same angular velocity as the Earth. We can make a simple attempt to calculate what that orbit will be. Remember that the centripetal force is provided by the gravitational attraction between satellite and Earth. A few minutes ago, we arrived at an equation for the velocity that can be rearranged to give the radius. R equals gm over v squared. Now, the distance a satellite travels in a single orbit is the circumference. So d equals 2 pi r. Now, if it takes time t to complete one orbit, v, the velocity, equals 2 pi r over t. Substituting for v, we get r cubed equals gmt squared over 4 pi squared. This equation looks a bit complicated, but in fact it enables us to work out the orbit of a geostationary satellite. Now we know the value of g, the gravitational constant, and m, the mass of the Earth. For a geostationary satellite, t is 24 hours, and therefore we can calculate the value of r. It comes out at 42,000 kilometers. That's the radius of the orbit, allowing about 6,000 kilometers for the radius of the Earth. Then a geostationary satellite will be about 36,000 kilometers above the Earth's surface. Now that's a lot higher than USAT, which has an altitude of 550 kilometers. Obviously, to put a satellite into geostationary orbit needs a lot more power. In the mid-60s, rocket technology had developed sufficiently to attempt to put a satellite into a geostationary orbit. The first one was called Intelsat-1, or more familiarly, Earlybird. It was positioned over the Atlantic Ocean in an orbit that in practice turns out to be 35,800 kilometers. By today's standards, Earlybird was a modest satellite, but it marked the beginning of an enormous growth in satellite technology. Earlybird was the first in a series of satellites known as the Intelsat series. There have been 6 generations of such satellites and several satellites within each generation. Each generation of satellites has brought an enormous increase in capacity. Intelsat-1 carried 240 telephone circuits. Intelsat-5 carry 15,000 telephone circuits and 2 television circuits. There are 11 satellites in the Intelsat-5 series. This is the latest generation of communication satellite, Intelsat-6. The satellites in this series can carry 44,000 telephone circuits and 3 television circuits. When its aerials are fully deployed, it stands nearly 12 meters high. This model can give us a good idea of the basic elements that go into a satellite. First of all, the whole body of this satellite is covered with solar cells, which convert solar radiation into electricity to power the satellite systems. These cells on Intelsat-6 produce 2.2 kilowatts of energy. Now, the lower part of the satellite is constantly rotating, and this helps to stabilize the satellite in space. The upper part of the satellite is always orientated towards the Earth, and its precise orientation can be controlled by signals from Earth. These dishes are the aerials for receiving and transmitting signals. Modern satellites use signals in an extremely high frequency range, about 4 to 12 gigahertz, that is, thousands of megahertz. Such signals are called microwaves. They're little affected by the atmosphere, and they pass straight through the ionosphere. There are two other major reasons for using such high-frequency signals. The higher the frequency, the more information that can be transmitted on the carrier wave. And the higher the frequency, the smaller, within reason, these dish aerials can be. Now, the signals received by the satellite have a frequency of 6 gigahertz and are collected by this dish. We can illustrate quite simply how the dish works. If a wave strikes a parabolic reflector, then the waves are brought to a focus. And so, by means of a parabolic reflector on the satellite, the microwaves are focused onto this part of the aerial. Now, the signal is amplified inside the satellite and then retransmitted down to Earth at a frequency of 4 gigahertz. By using a frequency which differs from that of the received signals, transmitted and received signals don't interfere with each other. Exactly the same principle applies in the use of a parabolic reflector in transmitting microwaves. The microwaves are transmitted through these horn feeds, which are placed at the focus of the parabolic reflector. Waves which arise at the focus of the parabolic reflector are reflected into a parallel-sided beam. This is how signals from the satellite are beamed to specific regions on the Earth. A modern satellite can transmit signals to Earth in a number of different ways. Let's assume that the satellite is stationed over the Atlantic Ocean. Signals can be transmitted on a global basis. That is, they can be received from anywhere on the surface of the Earth facing the satellite. As we've seen, the parabolic reflectors can focus the microwaves, and these are beamed into specific coverage areas. These areas, marked out in red, are known as hemi-coverages. The transmissions can be more precisely directed to specific areas known as zones. Here they are. This one covers North and South America, and this one Africa and Western Europe. Those of you who are observant will have noticed that there are two other dish aerials on the satellite. These aerials are receiving and transmitting at 11 and 14 gigahertz and cover two small spot beam areas. The spot beam areas are the northeast coast of America and Europe, the two areas of the world having the greatest demand for communications. Well, that's what's happening 35,500 kilometers above the Atlantic Ocean. Now, the same principles apply to the ground receiving stations. Parabolic reflectors are used to gather the signals from the satellites and to transmit signals to them. Only being on Earth, the aerials can be a lot larger. There are 3 satellite Earth stations sited in the United Kingdom. Goonhilly in Cornwall was the first to be built and was involved in the first Telstar experiments. Since those days, it has grown and now has 6 giant aerials. The second station to be built was Madley in Herefordshire, and this station has 5 aerials. The locating of such ground stations is no easy task, as the sites have to meet a number of specific requirements. For example, the location must be reasonably free from electrical interference, and the ground itself must be firm enough to support the enormous weight of the aerials. Just the moving parts weigh nearly 300 tons. There are also a number of environmental considerations which have to be taken into account, but the aerials must be as large as possible. The transmitting satellites are 40,000 kilometers away, and the received signals are extremely weak. Typically, the parabolic receiving dishes are about 32 meters in diameter. It's also essential that the aerial is kept pointing as accurately as possible at the satellite. When viewed from the Earth, a geostationary satellite like this one has an apparent motion. Not only is the satellite affected by the gravitational pull of the Earth, but also that of the Sun and the Moon. Furthermore, the Earth, which is not a perfect sphere, tends to wobble on its own axis. The net effect is that to an observer on the Earth, particularly an observer who's not on the equator, the satellite appears to move around in the sky. In order to compensate for this motion, the aerial must be constantly steered, all 300 tons of it. The aerials can be rotated about their horizontal axis as they run on a sort of circular railway. The aerials can also be tilted in the vertical plane by means of large rack and pinion gears. In the northern hemisphere, aerials are inclined towards the horizon, as the satellite's orbits are in the equatorial plane. Despite their enormous weight, a satellite receiving dish can be steered with great accuracy, and it's done quite automatically. A beacon signal is transmitted from the satellite, and if the receiving aerial strays off beam, then this signal will become weaker. The strength of this signal is used to steer the aerial. The signals collected by the dish are passed via a series of reflectors to the receivers. In this way, the aerial can be tilted and rotated through any inclination or angle, while the receivers are in fixed positions in the building below. Here, the signals are amplified and then retransmitted via landline, line-of-sight microwave, or satellite microwave link. The latest satellite ground station to spring up is in the London Docklands. Called Teleport, it's at the moment primarily concerned with the transmission of television signals to Europe. It's also the first major Earth station to be built in a city. The growth of satellite communications has been so great in the last few years that large companies are now having their own small Earth stations installed on their premises. These systems are designed to handle a range of business communications, such as audio and video conferencing, facsimile, and data transmissions. Satellite systems are now being introduced for specialist services. For example, the satellite Inmarsat was launched specifically to provide a maritime communications service. The satellite provides a microwave link between the aerials of British Telecom International ground stations and small dishes shrouded in weatherproof covers on the decks of ships. A vital link in obtaining both commercial and meteorological information or coping with a medical emergency. We must remember that while microwave communication systems make great use of satellites, microwaves can be used for direct line-of-sight communications between two ground stations. Remember at the beginning of this program, the link from Geneva? Once the signals had been received by the satellite ground station, they were then relayed to London via a series of direct microwave links which make use of small parabolic dish aerials. Such aerials seem to be appearing everywhere these days. Indeed, they're even turning up in schools. This parabolic dish aerial has been set up in the school grounds to receive information from Meteosat, a geostationary satellite which, as the name implies, gathers meteorological information.
Looks nice. It looks like cloud.
We all make use of satellites, whether it's phoning a distant relative, watching live entertainment, or receiving and studying the satellite signals themselves in our own classrooms.